For the last 4 classes, we were discussing about sigmatropic reactions under pericyclic subject, right? Sigmatropic reactions, what we saw in sigmatropic reaction is that we saw 1 comma sigmatropic reactions can be broadly classified as 1 comma n sigmatropic reactions and n comma m sigmatropic reactions. Under 1 comma n sigmatropic reactions, we were studying about 1 3, 1 5, 1 7 hydrogen ships. Then we started studying about 1 3, 1 5, 1 7 carbon ships. And then we studied about how this hydrogen or the methyl group should move, whether it is suprafacial movement or intrafacial movement, and we used our Woodward-Hoffmann rule for deciding that. And after finishing this 1 comma n sigmatropic reactions, then we slowly went into n comma m sigmatropic reactions, where we studied how a sigma bond can be moved through the pi system. Okay. And in n comma m sigmatropic reactions, we then studied 2 comma 3 sigmatropic and 3 comma 3 sigmatropic reactions. In 2 comma 3 sigmatropic reactions, we studied on many reactions like Stevenson's, Somalt-Asser rearrangement, and we covered many of the reactions. And then in 3 comma 3, we slowly studied about your Cope rearrangement. We studied all the aspects of Cope, right? How Cope reaction stereochemistries, we studied about them. Then we studied about oxy-Cope. Then we slowly went into their Aza-Cope system, and we did some examples on Cope rearrangement. After finishing Cope rearrangement, then we went into Claisen rearrangement, and we studied their synthetic utility of Claisen rearrangement. We studied different variants of Claisen rearrangement, like your Johnson Claisen rearrangement, Ireland Claisen rearrangement, and we studied some aromatic Claisen rearrangement. And then we finally ended up with studying 5 comma 5 sigmatropic rearrangements and 9 comma 9 sigmatropic rearrangement. So that's about the one important class of pericyclic reaction, that is your sigmatropic reactions. So from today's class, we will be trying to focus on cycloaddition reactions. This is another set of reaction which is broadly comes under your pericyclic reactions. So we will try to spend like another 2 or 3 class on understanding about cycloaddition reactions. So the broad definition, if you want to know about, it is like 2 unsaturated molecules. 2 unsaturated molecules undergoes an addition to form a cyclic product. This is your cycloaddition reactions. The best one is that you take an unsaturated system like your diene, and another unsaturated molecule is your alkene. Okay. And if you heat this reaction, it forms a type of cyclic product. Okay. So this is a class, it's a broad class definition of your cycloaddition reaction, like 2 unsaturated molecules undergoes an addition to form a cyclic product. But there are many reactions in which you can even see like 3 molecules or 4 molecules undergoing cycloadditions type of reaction. But as a broad definition, simple definition, we can keep like 2 unsaturated molecules undergoing an addition to form a cyclic product. So this is a definition about cycloaddition reactions. The another thing is classification of cycloaddition reactions. how we can classify cycloaddition reactions based on number of pi electrons that is involved in your reactions. Okay. Based on that we can classify your cycloaddition reactions. Fine. For example, like we can classify them as 2 plus 2, very important classification of cycloaddition, 2 plus 2 cycloaddition, where you can think an alkene reacting with another alkene to form a cyclobutane system. Okay. Here you can see it is 2 pi electrons and same way it is 2 pi electrons adding together to form cyclobutane system. This is 2 plus 2 cycloaddition, and then we can even think about your 4 plus 2 cycloaddition, where you can have your butadiene plus your alkene to give you a cyclic product. So, this will be a 4 pi electron system and this will be a 2 pi electron system. So, giving you a cyclic product. This is your famous reaction, this is your Diels-Alder reaction. Then we have like we can even have a system like this, where you have A, B and your C with your electron on your A. Again, if you see, this is 4 electron system, where you have 2 electrons here and you have 2 electron here. So, it is a 4 electron system with your alkene to give you a 5 membered ring. Okay. So, this you can call as you have studied this 1,3 dipolar cycloaddition. You have this reactions. Same way you can write 4 plus 4 cycloaddition reactions. So, basically how you classify cycloaddition reaction is that you classify cycloaddition reaction based on number of pi electrons interacts in the system. So, in the earlier case we have seen like 2 pi electrons and here 2 pi electrons interacts to give you a cyclobutane system, that is why we call as 2 plus 2 cycloaddition. In Diels-Alder we can see 4 pi electrons and 2 pi electrons. So, it is a more like a 4 plus 2 cycloaddition, clear. So, that is how you can classify the cycloaddition reactions. Now, before getting into understanding like 2 plus 2 cycloaddition and 4 plus 2 cycloaddition reactions, what we will do is that we will try to understand more about the mode of additions. Okay. So, what we will be trying to focus in this coming classes is that we will work on 2 plus 2 cycloaddition reactions, then we will study 4 plus 2 cycloaddition, in which we will concentrating more on Diels-Alder reactions and 1,3 dipolar cycloaddition. Okay. These are the 3 reactions we will be concentrating for the coming class. So, now we will just see the mode of addition, how the cycloaddition reactions happen based on your FMO projection, like frontier molecular orbital, how we can understand the mode of action. Okay. So, basically we call them as a suprafacial versus intrafacial cycloaddition. So, what this suprafacial and intrafacial means exactly? For example, I am taking a system like, say I am taking a molecular orbital, I am taking a molecular orbital like this, right. In another case, I have a system where I have like this. Okay. Now, if during the addition, the HOMO LUMO which we are talking about, the HOMO of one of the reactant and LUMO of another reactant which we are going to talk about, if this addition happens exactly on the symmetry lobes, that is on the same side face, okay, then we call this as supra. Okay. If our addition takes place in opposite one, okay, then we call this as an antra. Right. So, if it is in the same phase, okay, the same phase of your orbital with the HOMO LUMO, then you call it as suprafacial. If it is in one on the opposite phase, another is opposite to it, then you call that addition as an antrafacial addition. Much more to be very precise, for example, I will consider the for example, I am taking a system. Okay, this is not an alkene type of system, like just we say that is an N system, or like just a minute, much more to be clearly drawn. A system like this. Just to show that it is it's not a single, it's an N, this can be a number of carbons in between, okay, just to give that idea. So, now if you see this cycloaddition, okay, the HOMO and LUMO, the one is the HOMO, another is the LUMO, okay, you see they are happening in the same phase, okay, that we call as suprafacial cycloaddition, okay, suprafacial addition. So, how we call this? We can just say that this is pi, okay. We normally call as, you can put your 2 or n, because this is n system. So, I can keep it as pi n s plus another pi n s system, okay. If it is a 2 electron system, then you make it 2 pi 2 s plus pi 2 s, or pi 4 s plus pi 2 s, okay. This is your suprafacial, because it happens in the same thing. If we go and see how antrafacial addition will be, an orbital HOMO of 1, if you see in this case what happens, you can have one on their symmetrical loop, right, same size, but other case we will have in the opposite, okay. So, that will be antrafacial. So, this will be suprafacial and this will be antrafacial. So, how you write that? You write as pi n s plus pi n a, right. So, this is your addition. So, normally we call as antrafacial. Antrafacial cycloaddition. So, this is pi n s plus pi n a, because this is antrafacial and this is suprafacial. In this case both are suprafacial, okay. This is like a general term. Then we can slowly, so that's how you call cycloaddition. You can say the system undergoes a suprafacial cycloaddition or antrafacial cycloaddition. They can have pi n s plus pi n s, both are suprafacial, you call them as a suprafacial system, one suprafacial and another you call as pi n s plus pi n a system, depending of the things, right. So, this is the mode of cycloaddition based on your FOMO theory. Now, what we will do is that now we will slowly get into our 2 plus 2 cycloaddition. That is your first cycloaddition which we are going to. This is just an introduction. So, what is cycloaddition? How you can classify cycloaddition? So, cycloadditions are nothing but it is just an addition of your unsaturated molecules to form cyclic products. Classification, you can classify based on the number of pi electrons involved in the system. Then we have seen the suprafacial and anterofacial, same phase lobes, then you call as supra, which is opposite you try to say about anterofacial. And how to name them? Pi and s plus, depending upon your pi system, what number it is, 2 electron system, then you say pi 2, then whether it is suprafacial or anterofacial. So, that is a introduction about your cycloaddition reactions. Okay. Now, we will get into your 2 plus 2 cycloaddition reaction. We have studied that if you take an 2 alkenes, okay. I am not just specifying any condition right now, just if they combine to give you a type of cyclic product, you call this reactions as 2 plus 2 cyclic addition reactions. Now, we will see under what condition how this happens. If you thermally activate this reaction, whether it will undergo whether it is allowed. If it is allowed, then what happens, whether it is suprafacial cycloaddition or it is a anterofacial, whether it is pi 2s plus pi 2s or it is pi 2s plus pi 2a. In photochemical activation, what will occur? So, first we will try to understand that, then we will go and see the examples. Okay. So, we will say in heating, what you can see in heating condition, that is all or thermal activation, okay, how the orbitals look, because we know it is 2 plus 2. For example, we can take your alkene system. So, we will draw the HOMO, okay, of your one of your alkene. Then we will take the LUMO or of your another alkene system. Right, we can take the LUMO of another also. Now, see this, because this should be in the heating condition, right. This is the HOMO of one of your alkene and this is your LUMO. Whether they can do now what system, I can have this, okay, but this is not allowed. So, what we can say is that pi to s plus pi to s is not allowed in heating condition, it is not allowed. So, you cannot have this see most of the time if it is suprafacial, okay, it's the reactions are much more allowed, okay, it can go nicely. You have seen very rare examples where you can have suprafacial and anterofacial, that type of reactions are there, but if it is suprafacial it is much allowed reactions, okay. Anterofacial, one of the problem is that they have to be geometrically allowed, that condition prevails. We will say, we will take the same example, okay. If I want to do, if we want to draw like suprafacial and anterofacial for this type of system, okay. So, this is the HOMO of your alkene, okay. This is your HOMO, for example, I am considering like that, and this is your LUMO. So, now you can always have a chance of, if it geometrically favors, okay, you have a chance of making like this, right. Then you can say this is pi 2 s plus pi 2 a. So, if you generalize this, like you can say that in heating conditions cycloaddition reactions does not undergo your suprafacial, it is not allowed, but you can think about undergoing suprafacial plus intrafacial reaction. But the care here it should be is that it should be geometrically favored. If it is not geometrically favored, then this alignment of your suprafacial to intrafacial never takes place. So, most of the case they become forbidden, okay, unless the geometry allows them. That is the important thing you have to remember. The geometry should be possible, the geometry should be favored. Otherwise, you cannot see this. Okay. This is on your eating. Okay. What will happen if I photolyze this? So, under photochemical condition. So, same way we can write. Now, under photochemical condition you can. So, what happens, you will write now excited state HOMO, right, because you are exciting the one of the alkene. So, you will be writing excited state HOMO and you will be writing your LUMO of your another system. Previous case you were thinking about the ground state. Okay. Now, since it is photochemical you are exciting. So, you are generating a new type of HOMO and new HOMO that you call as an excited state HOMO. Okay. And now, you are writing about the LUMO. Now, in this case you can see the orbitals are aligned nicely to form your pi 2 s plus pi 2 s, which is suprafacial. Right. So, what we can say then, if you do 2 plus 2 cycloaddition, you do 2 plus 2 cycloaddition, so if you heat it, okay, your S plus A is completely forbidden, right. You can then say S plus S is completely forbidden when you eat, but you can see S plus A, but it should be geometry should favor. But if you shine light, S plus S is allowed. Okay, you can S plus A is not, is forbidden. So, like that you can, now you can finally generalize based on your FMO3, like heating, what happens, your S plus S is forbidden, S plus A is allowed geometrically if it is favored. Then in light S plus S is allowed and S plus A is forbidden. Clear? So, that is about introduction of your 2 plus 2 cycloaddition reactions. Now, we will just get into some examples and see whether we can use this idea. We will take the simplest example, like we will take your alkene system, like endyne system. Another same dyne, okay. So, if you photolyze this reaction, okay, if you excite this, what you end up? Yeah, first we will write the product. So, you end up with an cyclic product like this, right. So, how this reaction is, what mode of addition it is? It should be supra, right. So, we should call them as pi 2s plus pi 2s, right. See, that is very important, because you have to once we go to systems where you can generate your chiral carbon, then you should know whether the reaction is specific or not. Okay, that time your suprafacial additions are very important. In this case, fine, but we will go for some other examples where we can see that why pi 2s plus pi 2s is important. Okay. Same way, if I heat this reaction, what do you expect? So, what happens is that we should think about pi 2s plus pi 2a, okay, it should be a suprafacial antefacial, because you do not have this pi 2s plus pi 2s is forbidden in heating. So, it should be pi 2s plus pi 2a, but if you see these alkene systems, okay, they are more same, they are not geometrically favored, it cannot sit on each other like this. Okay. So, geometry does not allow, that is why what happens, there will be no reaction. So, you will have no reactions, okay, very good example to understand. So, it should but basically we should think about pi 2s plus pi 2a, but the idea is that since the geometry is small for them to CC to make a bond, it does not happen. So, you get there will be no reaction, but if you do the same reactions in light, you get a nice product. Okay. We will take the second example, like now what I am doing is that now sort of when you do a cycloaddition, okay, on this you will generate a type of chiral carbon, right. Now, you should know how your system is. If I photolyze this, first thing comes into your mind is that it should be supra, right. So, it should be pi 2s plus pi 2s. So, it should be the same phase, it should come in the same phase. Then how your product should be. If I write the product, this is one side of my alkene, okay, that is my methyl, I have my methyl here, this is my the alkene part, okay, and this is my phenyl part which I am going to write. So, it should be most of the time I get my phenyl here with my hydrogen on one side, okay, and I can get my CN here with my hydrogen on one part, right. You can get a type of specific product, or it can be other way around. If you can say that it is I can get in like CH3, CH3. Right. You can also think about this first. So, this tells that reaction is proper, comes in the same phase to make your bond. Okay. So, you are not changing any stereochemistry here. Okay. So, you get a very nice products. If it is like a trans, you get in the same type of product here. If you take like this is in this case it is cis, then if you take trans, you might end up then with the two different that is good. Same we will take another example, which is your third one. Just a case like you have an alkene type of alpha beta E node. Okay. So, you can have your 2 plus 2 cycloaddition here. Yeah. So, this reaction, once you photolyze, you can write pi 2s plus pi 2s. So, we want to have the stereochemistry because it comes in the same phase of that. So, your 2 CO2 should be, yeah. So, you can then write, first we will finish the product. So, your CO2 Me and you have a CO2 Me, then you have your hydrogen and you have your methyl. Right. So, this is another type of example which tells about superficial, how it should be very precise in additions. We will take some interesting examples which will be which you guys have studied this example. Right, I think we have just seen this example when we were talking about align pi system chemistry, right. So, when we photolyze this, we can say it undergoes pi 2s plus pi 2s. So, I have to draw your product. Nicely undergoes quadricyclic systems. So, another example which we will be interested of speaking about is this we have studied, where we have studied this example. Where we have studied this type of your benzene, divar benzene types. It is a methyl substituted type of divar benzene, and once you photolyze this, again undergoes a nice pi 2s plus pi 2s system. Can you draw the structure? It will be interesting to draw the structure. Like prismine type, it will be like prismine. So, then you can put your methyls here. Okay. So, you get this type of nice reactions. Okay. So, these are very good reactions of your cycloaddition of under photochemical conditions. Okay. Now, what we will do is that we will slowly get into your thermal activation, where you can end up with your pi 2s plus pi 2a system in 2 plus 2. So, we have studied that geometrically it should be allowed. If it geometrically gets allowed, then you end up with a nice type of pi 2s plus pi 2a system. They are very good system. Any idea what it can be? What type of 2 plus 2 cycloaddition where you end up seeing pi 2s plus pi 2a? You have studied this in detail. Your ketene chemistry. Okay. Ketene cycloaddition, most of your ketene cycloadditions with alkene, ketene cycloadditions with your imine, famous Staudinger equation reaction, then your ketene addition with your carbonyl compounds to form beta lactams. All these reactions goes by pi 2s plus pi 2a chemistry. Okay. That is pi 2 suprafacial plus intrafacial. So, what we will do is that we will study in detail, okay, ketene or I can say cycloaddition reactions of ketene. So, we will try to understand now this in detail. Okay, cycloaddition reactions of ketenes. First, we will see what that reaction is all about. You can take a nice type of ketene. Okay. Then you can take your alkene. For example, I am taking like a much symmetrical type of alkene, and you just thermally activate this. Okay. You end up with a nice product. Yeah. Okay. So, it is basically it is a 2 plus 2 cycloaddition of your C double bond C and C double bond C. Okay. C double bond C of this and C double bond of these are the basically system involved in that. Okay, to give you the cyclic product. And if you see what our rule, it says that it should be heating, means it should be pi 2 s plus pi 2 a. Okay. Now, we will see that how this chemistry happens, how it is geometrically allowed, okay, why it should happen this, which is not happen in simple alkene. If you take 2 alkene system, it never undergo heating, no reactions, but in this case ketene chemistry, most of your reaction goes by suprafacial plus intrafacial chemistry. So, first we will see why it should happen. Okay, we will see the geometry, why it allows by orbital picture. For example, I am taking my alkene, you can consider the HOMO of your alkene. So, for if you want to write, I am taking this as your for example, your alkene, if you want to write it, okay, like this type of system. What you do is that you just rotate this 90 degree, so that your 2 lobes are seen like this. Okay. So, what it is I am saying exactly, like this 2 lobes which I am talking about here, okay, that you see from the top. So, its geometry is like that. So, you see the 2 lobes here, clear. Now, what happens is that now your ketene comes, okay, and sits the ketene which we are talking about can a carbon, okay. You are talking about the LUMO of the system, okay. I have my carbonyl. So, this will be the HOMO I am talking about. I am talking the LUMO of this. So, it should be okay. So, now the geometry is like that. So, you have an alkene, it nicely sits here, okay. So, you can now you can easily form a type of bonding nature system if you want. Or even you can write it in other way around, that it should be white and white, you can do it. So, it should be supra and type of, because of sitting nature of that, okay. It can be white here, so that you can get the white stuff from here and make a bond, okay, fine. So, that is why the whole geometry allows this system to do your pi 2s plus pi 2a chemistry. Okay. So, any doubt in this? Why ketene chemistry happens nicely? Because of this is the geometry I am talking about. Okay. So, what we will do is that now we will try to understand this ketene chemistry in detail. What we will do is that first we will take synthesis of ketene chemistry, we will see how we can synthesize ketene. Then using our so called FMO theory knowledge, we will see how it reacts with alkenes, how it reacts with your aldehydes, how it reacts with your imines. Okay, we will do one by one that. Fine. So, first we will see how we can synthesize ketenes, that is very important. You can know that the first normal method people check for synthesis is your and okay, this is your chloride. So, you can take this is thing acyl chloride and you use your triethylamine and you know what happens is that your triethylamine can okay, this can abstract your hydrogen, okay. Giving you a nice right, you can get nice synthesis of ketene. This one normal synthesis people do, you take an acyl chloride type of system and use base, you can get your ketene nice. Another synthesis of ketene is your using your ester, study that you can even same system instead of acid chloride, if you want to use like an ester type of system OR. Okay, same way you can use your lithium based bases, okay. Then you end up with your enolate type of system. O minus and that OR, at this type of systems, right. This can again push it back to give me so it's better to know how to make ketene type of systems, right, because when we do synthesis earlier case what type of elimination it is, this one, this is your E2 elimination, okay. As an E2 elimination which happens nicely. In this case that is more nice chemistry for that. What type of elimination it is, this one. This is your E1CB, okay. E1CB elimination you can happen. So, these are nice synthesis, like you can see elimination reactions much happening here. We have one more system where you can even use, people use dichloro systems, like you can have like 2 chlorine systems. So, what you use, because this is not commonly used is you use, this can be done in presence of zinc, na? Like yeah, if you have zinc you can do this chemistry, little bit base is required for a, like if you have a so since you have zinc chloride, okay, then you end up with your nice ketene. This is this you can see with the zinc type of regular, this normally people use it, okay, type of you have an alpha chloroacyl chloride systems and you use like metal salts, end up with your ketene chemistry. Another one which you have studied, which on thermal activation or by photolysis you can generate your ketene chemistry. What is that? You can thermally activate and you can generate. You can end up with even with the singlet carbon type of systems, which you have studied also. You can get your diazo systems where you can heat it or you can photolyze, you end up with a carbon, then you have a 1,2 alkyl shift leading to you ketene chemistry, that you have studied that in our earlier classes. Just we will write that. So, if you take this type of system, if you photolyze or thermally or even if you can thermally activate this, you can end up with your carbene, right, or even you can say, people other way of writing is that can R, this can be written like this also, O minus with your positive charge here, right. Say that you can get it up here. Now it's type of rearrangement, na, which you have studied. You can have a rearrangement here. So you can then think about getting your okay. This is these are 4 methods. There are other methods, but commonly used are these 4 methods by which you can generate your ketene. Okay. So, one, we can use your acyl chlorides, or you can use your esters, or you can use your alpha chloroacyl chlorides, or you can think about your diazo systems where you can thermally activate or heat, you end up with the ketene generations. Okay. So, it's so these are the 4 good methods of your ketenes. Now, what we will do is that now slowly we will understand the reactions of, since we know now synthesis of ketenes, now we will slowly get into the reactions of ketene chemistry. Okay. See, there are a number of reactions, but we are going to concentrate more, which is 2+2 cycloaddition. We are concerned more about 2+2 cycloaddition reactions. For example, if you have a ketene like system, like if I have a general ketene, if I treat with an alkene, okay, so it undergoes a type of 2+2 cycloaddition. Okay, we will get in detail for other chemistry. Just we it's a type of summary of your ketenes, what ketene can do. Then we will get into individual chemistry. Okay, so you end up with a product like ketone, and this is your ketene part, right? And then this should be your, can talk about this chemistry. We will talk about this chemistry in detail. Okay, alkene chemistry. Then, if you want to treat it with carbonyl compounds, want to treat it with carbonyl compounds. Okay, you end up with your beta lactone. That also you can, nice reactions. If you want to treat it with imine, okay, then you get beta lactams, right. This is your famous Strongyniker equation, right. So, this all chemistry, these three chemistries happens in heating condition. Okay. Now, we will go in detail and we will understand how this chemistry goes. We will first take alkene, we will study them, then we will go to imine chemistry, then we will go for carbonyl chemistry. Okay. So, that is for this class. We will end our class right now with this.